Okay. Well, good morning, everybody. I think we'll get started. I wanted to let everybody know that I will be recording this and then we'll make this available to anybody who requests it. So thank you very much all for coming. My name is Pambos Anastasiou. I'm CEO of IQ3 Solar. Just as a reminder, if you don't mind, please put yourself on mute, and at the end you will be given a chance to ask questions, and then you can unmute yourself. So just a reminder for that. So this is the sort of at the end of the pre-seed funding that we have received, and we're giving a presentation for that will cover the origins of the company, what was our motivation, what is our mission for starting the company, give a little bit of the history, and then we'll go into the technology behind it. In a nutshell, the world is moving away from fossil fuels into renewable energy. They are doing this to reduce pollution, to reduce the strain on the resources of the countries, and to actually create independence from fossil fuels and sources that keep you tied to different geopolitical events that could affect the economic growth of a country. So this road from fossil fuels to renewables actually has much room for growth. As we can actually see, this is a recent graph that I pulled out from the International Energy Agency. It shows what is the worldwide electricity sources, and you can actually see that coal, oil, natural gas, nuclear dominate. Hydro is also very important for those countries that have hydro. This is a renewable energy, but it's not for everybody. And then we can see solar and wind. And solar is actually worldwide. It's sitting at around 3.5%. Okay, so there's a lot of room for growth, and this is actually a one-way road. We're not moving back. A recent pledge that was given in the COP28. This is a direct statement from the European Commission President Ursula von der Leyen, where the goal is to triple the renewables by 2030. So we expect a lot of growth into this field. Solar photovoltaics are emerging as one of the dominant solutions for this, and they will play a very key role in this energy transition. And the reason for that is that they have some unique advantages that other renewable sources don't have. They are very versatile. You can install them from the home to the neighborhood, to the parking garage, to the field. So because of this versatility, and because they can easily be deployed, they are actually gaining quite a bit of prominence. Another thing that I would like to mention is that they are a global source. People tend to think that you need them you can actually only install them in countries that have a lot of sun. But in reality, even countries that traditionally we don't associate with being very sunny, they actually have quite a bit of potential. Even UK, all the way up UK, has itself solar potential, and they are off by a factor of 2.5 from Cyprus. Obviously, Cyprus has even more potential, but you can install PVs and they can make sense even in countries such as UK, Germany, and actually all over the world. So they are not just for those places that we think that they are sunny, but they can actually be used all over the world. And obviously, the more sun you have, the lower the temperatures you have, the better. But the difference between Cyprus and Germany is only a factor of 2 in efficiency, roughly. So this actually makes them very attractive. However, photovoltaics do have a number of challenges with them that have to do with their failures and degradation modes that are actually decreasing your output power. So it's not just the sun, it's not just having very efficient modules, but it's also ensuring that those modules work in optimal conditions and they don't develop faults and degradations that reduce your output. Now, how do you actually solve this challenge? One way is to do inspections, is that you have manpower that goes in, goes to the location, and looks at them, maybe with various instrumentation methods. The other one is to be looking at data. Okay. However, both of these solutions and both of these approaches have limitations. Photovoltaics tend to be a lot of times, especially for large installations, remote. They are not easily accessible. They are in remote locations. That's number one. The second one is that a lot of the degradations are actually hard to identify. They're not that easy to see. And the third one is that you have really a large volume of data, along with the data being very noisy. So what do you need to do? You need to actually develop solutions that are automated, meaning that they work 24/7 on their own. They grab the data, they analyze it, and they give you the warnings. They identify the errors by themselves in a very sophisticated manner, and they identify things that even with some instrumentation and even with the naked eye you cannot actually physically see, because they are degradations that are actually hidden underneath that performance that eventually they will cause bigger problems for you. And then a third one is you need something that turns your maintenance from reactive to predictive. So you need to have ways to predict the performance and predict the maintenance that your PVs are going to need. And this is actually how we were developed. This is our vision, is to develop best-in-class tools, software and hardware, that optimize and make the PV ownership and PV production autonomous and independent of human intervention. We were founded in 2022, but our history goes a little bit behind that, starting from the University of Cyprus, where we received Cyprus seeds funding. This is some of the work that Michalis did. In 2021, that is when we were filing for patents, publishing the work. And then when we received the funding from the Research and Innovation Foundation, the company was founded at the end of 2022. We started with the goal of developing these tools and bringing them to the market. In 2023, we actually have been focusing on product development. We have received quite a lot of recognition for our work, and we are on beta launching right now. We have actually launched in 2 sites where we're monitoring very carefully what, how our system is performing and what type of insight we can actually give to the owner. But of course, our plans go beyond Cyprus. We have global aspirations to launch this technology beyond Cyprus. What is the solution? The solution, actually, you would hear more from Andreas and Michalis. It consists of hardware, as we said, a sensor that gets installed at the PV park and makes measurements to identify these type of degradations, and then monitoring and forecasting predictive maintenance algorithms that grab data from the park, from meteo stations, analyze them, and then they give their results to the user through an interface that we have developed as well. So our value is that we identify early, we allow planning, and this allows for repairs to be done timely, and that overall brings an overall increased revenue for the owner. So we are moving from reactive to predictive workflow. We have developed a platform that shows you, your performance and also gives you an insight on how your system is doing. On the background of this is what, part of the front end. But on the background, you actually have a number of very sophisticated algorithms that are running. And the sensor here is one of the installations. You can actually see one feature is this little battery. And this actually, the way that the sensor works is that it charges and then it does the measurements at night. So it is low voltage, kind of an autonomous system. It is plug and play. It uses standard connections between the module and the inverter. We have been, recognized from our work. This is a picture of us at a deck. This is the Industrialized Association of Cyprus. We received this very prestigious recognition. We were runner-up. And last year, we also received this Cyprus Entrepreneurship Competition Award, given only to one company per year, Cyprus, all Cyprus countrywide competition. So we are very honored by this recognition, and we are ready to move on to the next steps, which is to bring this to a wider audience. So thank you very much for your attention, and we would hear now from Andreas and Michalis, which they will go into a little bit more detail into the technology. And at the end, I would say we can open up the floor if there's time for questions for all of us. Okay. So with this, I would like to thank you for your time, and I will end my presentation. Andreas, would you like to share screen? Or you prefer I do it?
Michalis, if you would like to go first, then yeah. I will explain the software.
Okay, let me share my screen. You see the presentation in full screen?
No.
Okay. When you do it on slideshow.
Make sure when you share entire screen, not window.
Okay.
So.
Now?
Yes, we can.
Yeah.
Present.
Okay, Michalis Floridis, and as Pambos said, I work on the PID sensor during my PhD at the University of Cyprus, and the sensor was patented in the USA and Europe. So the sensor is to detect potential induced degradation, PID. PID occurs usually on high voltage PV systems, and the PID progresses slowly. It could take more than a year for a 5% power loss to occur on the PV modules. Detecting PID with PV inverter data analysis methods, it's not detected at an early stage, and it can take more than 5% power loss before it's detected. And this lowers the energy production, and it has an impact on the revenue of the owner. PID, to identify PID, we developed a sensor for the detection. It can detect PID at less than 1% power loss, which means before the power modules lose 1% power. It's a non-intrusive method. It's automated, and there is no need to remove the modules from the installation. And it is 5 times more sensitive than the data analysis methods. And as you can see from the picture, our method detected, in this example, our method detected PID at day 7, while a conventional method detected it at day 49. The way it works, we select some modules, we install the sensor, we monitor them, store the data in our online server and the database. We do the analysis, and you can see the results from our online platform. The system architecture in a PV system is we install the sensors, as I said, at selected modules. The sensors communicate wirelessly with a gateway. The gateway collects the data and sends them over Ethernet to our internet database. We'll see later how more technical specifications for each component. So the sensor operates from 18 to 50 volts DC, which is a typical PV module output voltage, and its operating current is less than 50 milliamps. And the connectivity is wireless, and the sensor measures PID degradation at night without interrupting the PV production. And in addition to PID, we added the features of measuring the PV string current and the ambient temperature during daytime, which are used for further fault identification. The installation is relatively easy. It's a plug and play. No additional wires are required. There is no external power required. The sensor takes power from the module, charges an internal battery for operation at night. And the sensors are mechanically mounted on the metallic structure of the PV system near the desired PV modules. A metallic bracket is provided for that. How the sensor is connected to the module? It's easy. We choose the PV module we want to monitor. We unplug the module from the PV string and plug into the two connectors of the sensor, and then we plug the PV string to the other two connectors of the sensor. So in total, the sensor box has 4 MC4 connectors on it. Now for the gateway, we need an AC voltage from 100 to 204 volts. It consumes little power, and it connects to the internet over Ethernet. The gateway collects all the data from the sensors and sends them to our database. We did some tests. Here you see the installation from test site 1. It was 174 kilowatts peak PV system in Aglanja. We didn't install the sensors for the full park, but we selected 4 strings, and we installed 5 sensors and 1 gateway. This is our second test site. It was a 30 kilowatt PV system in Strovolos. It consists of 5 strings. Thus, we installed 6 sensors and 1 gateway. Here are some results for the PID detection from test site 1. In blue, you see our reference measurement. One of the sensors does a reference measurement, and the others are used to detect PID. With the red color, you see a PV module with PID. As you see, its reading is lower than the reference. It's below the detection threshold, so we know it has PID. And in on-range, there is a PV module. It's an example of a PV module without PID. And as you see, the measurement has near the reference and above the detection threshold. For test site 2, again, the blue is the reference. The The orange shows a PV module without PID, since the measurements are close to the reference. For these sites, we didn't detect any modules with PID. So this is for the PID sensor. Thank you. Andreas will continue with the data analysis methods.
Thank you, Michael. Can you see my screen now?
Yes.
So, good morning, everyone. I'm Andreas Livera, and I will talk about the software algorithms, basically the different technologies that we integrated in our platform for early fault detection. Just a brief introduction. We've seen a recent report from Kilowatt Hour Analytics showing that 8% of the PV yearly production is lost due to inefficient operation. And if we translate this to money, it's approximately 10 billion lost per year. And the root causes of this problem, the first one is because we have too many and very noisy data. So data interpretation is difficult. The second one is that different fault types and degradation mechanisms go undetected within the PV system, and there are no tools to detect them at early stages. And the third one is that there are no automated action recommendations, meaning we get all those data, but there isn't any translation to what operators should do in order to minimize the power losses. So what we propose is the IQ3 solar solution, which is basically consists of two parts: the hardware, which is the patented sensor, and the software part, which are the software algorithms. And the combination of two can be used for early fault detection, action recommendations, and predictive maintenance. For the software part, we basically used different machine learning and statistical algorithms for data cleaning, fault detection and classification, for forecasting, and for maintenance. And why we decided to use such data-driven methods? Because the PV plants, they generate large amounts of data. So we have the available data to work on it. And if we interpret those data efficiently, then we can get some meaningful insights and information about the fault root causes and instructions on what we should do. Now we are going to move on and see the general approach for fault detection. This is for the data-driven software algorithms. First, we acquire the field data. These are the meteorological and electrical data. Then we do some data cleaning in order to have a clean data set. And then we move on with the analysis using the different software algorithms. Finally, we provide some data insights and information about the energy loss, the fault root causes, and some recommendations in order to maximize the PV production and minimize the power losses in the PV system. This is a more detailed methodology on the approach we are following for fault detection. Once we acquire the field measurements, then we do some data quality assessment. Once the data are clean, we move on with predictive modeling in order to simulate the electrical characteristics of the PV system. And then we have the failure detection and performance loss routines, where we detect different performance losses and faults. And finally, we have the recommendation engine, which is basically they estimates the energy loss. It sets some criticality values for the faults, and it recommends some actions to be taken. Now I will move on and explain some of the parts of this approach. The first one is the data quality assessment. Here we do periodic data checks to identify duplicate records, missing data, erroneous values. We can also see here the availability of the data, and we can also do some data filtering, aggregation, some data deletion, and inference technique in order to reconstruct the given dataset. So here we can see some exports from our platform. We have the raw measurements along with the predicted measurements, and also we can see here the availability of the different measurements. From this stage, it is worth noting that we can also detect different types of faults, such as outages, and we also have a summary that tells us which data points are of good quality, which are missing, and which are erroneous. Moving on to the second step is the predictive models, where we have different parametric and digital twin models for simulating the PV electrical characteristics. Here we simulate the DC power current voltage and also the AC power. And here we can see some exports from our platform that we use the different models to simulate the electrical characteristics of the PV system. Moving on, the next step is the PV performance loss models. Here we integrated different statistical models in order to detect soiling and degradation. And here we can see an export from our platform that shows the degradation of the PV system using a linear method, and also the soiling intervals over the monitoring period. Then we moved on to the fault diagnostics and the energy loss stage. Here, basically, what we have is different algorithms that can indicate the health state of the PV system, along with some algorithms that indicate the underperformance incidents or the faults that occurred in the PV system. Along this, we have also an analytical method that gives us the energy loss, the yearly production, along with the energy loss estimation. And here we can see some screenshots about the produced energy for the test PV plant, its losses, and what it should be the theoretical output energy. Moving on, we can use also the previously developed digital twin models in order to detect some discrepancies between the modeled and the measured values. And by comparing those values, we can see the energy loss for each timestamp. We have the actual power, that is the power measured from the PV park. And also we have the model power that here it is from a digital twin model that estimates what should be the power of the system. Moving on, we have our recommendation engine that in case of faults, it provides some recommendation. In this figure, we can see it was during normal PV operation, so the engine did not detect any faults for the specified period. However, if we move on and see this picture here, we can see that over this specified period, the recommendation engine detected several fault types, and here it summarizes the faults, along with some recommendation on what the operator should do in order to fix those issues. So to sum up, we have designed a software as a service platform that integrates the hardware PID sensor along with some software algorithms, and the scope is to enable the early fault detection in PV systems. For the software part, we integrated data quality algorithms along with fault diagnostics and PV performance loss models. And also a recommendation engine that provides actions on what operators should do in case of faulty PV system operation. For future work, we have already developed additional software algorithms and functionalities, and we plan to integrate those into the platform in order to make it more intelligent and smart. And by doing this, we could schedule the operation and maintenance activities, handle intelligently detected faults, predict the faults, and this would lead to reduce O&M cost and, of course, increase energy yield. With this, I would like to close my presentation, and I would like to thank you for your attention.
Thank you very much, Andrea. We have a few minutes, and I wanted to do something that a lot of people tell you not to do, which is to do a live demo. Okay, I don't know if Mikhail.
Yes, I'm here.
Are you ready?
Yeah, I can do a live demo of the platform to show our current progress. Let me just share my screen.
And then we'll take questions. So let's do a. You guys can see this live.
Is my screen showing?
Yes.
Yes.
Okay, so this is the IQ3 Solar Watch platform. We built this platform using modern technologies like React and Next.js. Here is the dashboard where you can see all the available PV parks. You can see we have a couple of them. And if we select one of them, for example, Park 18, you can see all the available tabs that Andreas showed before. We can start with the raw data, which shows us the data for today. We can actually sort them by week or by month. And you can see all the values for every day. The next tab is the data quality. As Andreas talked about, this shows about the quality of the data we collect. So if we have missing data points or we have data that's outside the range of what's considered acceptable, we have a table that shows all the values that are missing or are corrupt, and of course the good quality data points. We can select the range that we want to filter, and we can see the graphs. We can select different data points that we maybe want to check. For example, all data points. We can see we have all the data except the temperature of the ambient air. For the next tab, we have this tab which is called PV performance losses, which I will try to run, but it will take like 1 minute because it needs to calculate a lot of data.
By the way, I should have introduced Michalis. Mikhail has been working with us on software development for 6 or 7 months, and he's actually right now in Greece. So I wanted to give at least an introduction to Mikhail. Thank you for doing this on a very short time, Mikhail.
Okay, here you can see the results of the calculations. You can see every data point individually. I won't go much into detail because Andreas already explained what everything does. The next tab we will see is the PV performance monitoring. This is the performance ratio of this year. You can see the performance ratio for every month until now, and also a table that shows the values per month. Here we have the fault diagnostics tab. As Andreas explained, we have an algorithm that tries to match what the PV panels should produce. So we have the measured data point, which is the actual measurements from the sensor, and also the predicted value. And we plot also the absolute difference, so we can see if there are any faults that happen for every data point. And we also have the energy loss analysis, which is a plot for this year that shows the DC power that was actually measured versus the predicted DC power. So we can see what kind of energy loss has occurred based on our prediction. And we will see also the yearly production. As you can see, the theoretical energy that should have been produced and the actual produced energy, and the losses also in percentage format for the year 2024. And the last tab what we'd like to show you is the digital twin. It is maybe the most sophisticated tab yet because it uses machine learning algorithms to actually make the predictions. As you can see, both lines follow very closely. It's a little bit similar like fault detections, but instead of using an algorithm, we use a machine learning model that trains on the data directly from the PV park and makes predictions about the power. And that's all I'm gonna show you. This also the difference between the predicted and the produced values, and a table that shows everything. Okay, that's all. Thank you for your time. If you have any questions, I will gladly answer them.
Okay. Yeah, thank you very much, Mikhail. Doing a live demo is always challenging, and this went very well. So thank you. Thank you for doing this in a short time. And I wanted to open the floor now. We are a small group, so just you don't need to raise your hand. Just unmute yourself and ask.
Thank you guys for the very insightful presentations and the live demonstration. It was very interesting to see the work you have done. As a team here at Avio Power, we are interested to see your findings for utility scale systems and explore potential collaboration opportunities.
Thank you. Is there any? I also see Mr. Christos Triteos.
Christos is a colleague of ours.
Okay, so he's part of the team.
Yeah.
Okay, I wanted to open the floor also for questions from Christos. If he had some comments or some questions.
No, it was a very interesting that you say about the PVC systems. Very and I didn't, and some of them I didn't know them. Thank you for all this great opportunity to see these presentations from you. And that's it. I don't have any questions. It was all perfect.
Thank you. If there's no further questions, then I will close this meeting. I would like to thank very much Andreas, Michalis, Michail, and everybody who helped prepare this and all the work that was done, and also Spiros, who was on the background supervising and advising Michail as well, and giving input. So I would like to thank our guests for taking their time out of their busy schedule to be here. So thank you very much, and I'll be sending a link, Haralambe, to that you can share.
Great.
Okay.
Thank you.
Take care, everybody. Bye bye.
Thank
Keep
you.
up the good work,
Bye.
guys. Bye.
Έλα ρε, Ανδρέα. Να σβήσεις τα
Πάμε,
με το
πάμε.
Σοδωρικό.